All right, next up we have Team 2. It's my pleasure to introduce Cardion.
Hi everyone, we're Cardion, and we're excited to present our product, a rechargeable system for pacemaker batteries. I want you all to imagine being 80 years old and told that you need your 5th pacemaker replacement surgery, not because the battery has failed, but because the battery is dying. Each of these surgeries comes with worries, like risk of infection, scar tissue buildup, and tremendous increased healthcare costs. And with age, each one gets harder than the last. There's 3 million people in the US currently living with pacemakers, and 600,000 more are implanted every year. Pacemakers are used to not only pace the heart, but also to send data to clinicians. And due to this, they have a battery life of only 5 to 7 years. This means every 5 to 7 years, $20,000 is spent on a replacement surgery. This makes an imminent need for a longer lasting solution to pacemaker battery life. Pacemakers send timed electrical impulses when the pacemaker notices that the heart is beating too slowly or too irregularly, and they do so through thin insulated wires called leads. These leads are controlled by the pulse generator, which contains the battery and is implanted in the shoulder region. For 75% of pacemaker replacement, it's again not because the device has failed or degraded in any way, but because the battery is dying. And that's why we developed Cardion. Cardion is a rechargeable pacemaker battery and a specialized third lead. Our pacemaker battery integrates directly within existing pulse generators, and our specialized third lead attaches directly onto the heart to capture the mechanical motion of a heartbeat. Our system works in 4 key steps. When we place the device, our specialized third lead goes directly onto the heart and captures the mechanical energy of a heartbeat. This is the energy that's being converted into electrical energy and then is being used to replenish the battery. Throughout all of this, we're monitoring the system on our patient and clinician-facing UI to make sure everything is going according to plan. And the system continues to repeat itself to give us a battery life of over 20 years, way longer than the normal 5 to 7. When we look at the normal standard of care, we see that 5 years after implantation, you need a replacement surgery. Another 5 years goes by, another replacement surgery. 15 years goes by, and so on. With Cardion, we mitigate the need for these risky and expensive replacement surgeries by having a functional period of over 20 years of battery life.
In order to accomplish this, we needed to meet 5 key specifications. Our goal was to design a battery that could last over 20 years while remaining compatible with all heart conditions, unlike dual chamber pacemakers, which are primarily designed to only treat bradycardia. We also prioritized patient safety in limiting tissue heating while recharging, and targeted affordability, keeping projected costs below $2,500. Our device is designed to be small and lightweight, making it ready for implantation into current pacemakers. And current devices out there don't meet all of these specifications. The Medtronic transvenous pacemaker and startups CareDAC and City Labs are either focused on improving battery life or on the compatibility and implantability side of things, making Cardion the only system out there that actually simultaneously and successfully meets all of the necessary criteria. But in order to reach this point, Cardion went through multiple iterations. Our proof of concept was very simple. We used a low power generating circuit that was mounted onto a breadboard and connected to a basic waveform interface to show that our piezoelectric material could generate electricity when being pressed on by a finger. We further expanded on this in our minimum viable product, where we used an energy harvesting chip that was able to get this energy from our mechatronic heart model that we built alongside an internal dashboard and physician-patient facing user interface. Now for our final prototype, we have a custom PCB that is able to maximize the efficiency of the chip and miniaturize the system as a whole. We also have accurate battery lifespan estimations, and we have an improved heart model that is able to be used for accurate testing. And now we're able to use all of this together to transmit data simultaneously and in real time over Bluetooth. Here we can see our progress from POC all the way to the final prototype, where before we had a very large circuit connected to an Arduino Mini, and now we were able to condense this fully into the PCB, which is housed inside of our biocompatible casing. And this device is meant to be small enough that it can integrate with pacemaker seamlessly, and is actually small enough that it can fit inside of the pacemaker. And this together, along with our user interface, makes it simple for patients and physicians to track its performance.
So the key to our whole, is this not? Thank you. So the key to our whole system is our piezoelectric material. We specifically went with a polyvinylidene fluoride-based material because unlike other piezoelectric materials, this one is lead-free, which makes it biocompatible and perfect for our use case. Our material also flexes. So whenever the heart pulses and it beats, the material flexes alongside with it. And every single time it does that, it generates an alternating current, which is then sent to our circuitry. This piezoelectric material is securely attached to our heart and then connected to our pacemaker in the form of a third lead. Whenever an alternating current is generated due to the deflection of the piezoelectric material, charge is sent directly to our circuitry, which is housed inside the pacemaker, and the pacemaker can then use that for downstream applications. Now, in its current form, it's not very useful because it is alternating current, so the first thing our custom PCB does is rectify to direct current before sending it through the chip. This chip then does three main things. It'll boost the voltage to usable levels, it'll provide a clean, clear, and stable output, and it'll also charge a supercapacitor for redundant storage. Our custom PCB also allows manufacturers to set the multi-power point tracking rate and the output voltage by changing several key resistor values.
In order to validate our hardware outputs and generate data, we've developed a software stack with the goal of being as energy efficient as possible. We are recording multiple analog voltages across our system and then sending them to an internal interface through Bluetooth Low Energy, where we calculate key performance indicators such as remaining battery life and expected battery lifespan. These are then delivered to an external user interface so that patients and users can access them easily. We are currently recording 4 analog voltages in order to measure our energy that we are harvesting, the energy that is being outputted from the PCB, the energy being stored in our supercapacitor, as well as the remaining energy in our battery. And we are able to record these data points in order to calculate our lifespan, which is a simple calculation of taking our remaining battery energy and then dividing that by our moving average of our system's energy usage. We've also incorporated an MCU selected specifically for its small and low power metrics. It is able to transmit signals through Bluetooth Low Energy, and it's also PCB compatible. While we're currently using an Arduino, we've also sourced the actual microchip, which would be even more power efficient once incorporated. And finally, all of these metrics are sent directly to a user interface, which is browser-based and designed specifically to be as easily accessible as possible. It also displays essential information such as the remaining battery life, as well as your remaining charge to indicate when the next replacement surgery would be necessary.
Now that we've shown you our device, how do we actually test it without implanting it into a human? To do this, we created a mechanical heart model that simulates a human heart, both in terms of the outward force it's able to produce and in terms of heart rates it's able to simulate within physiological ranges. With this testing setup, we want to first test that we have net positive power output. We did this by measuring the power output from our generating circuitry and also measuring the power needed to power the circuitry. In our results, we found that this black line shows the power generated by our circuitry and the red line shows the power needed by our circuitry. So we do have a net positive energy generation, so we can replenish the battery. Given that we can generate energy, now we wanted to test that our battery can accurately be measured. So we did this by using a test battery that we depleted with a resistor and then connected that both to our UI and to a multimeter. We found that not only were we able to replicate battery drain with this setup, but also that our battery voltage is accurately being recorded as the two lines follow the same pattern. Overall, these results show that Cardion is a pacemaker battery of the future. We have successfully attached our piezo material to our heart model, and with a third lead have connected to our circuitry that has a net positive power output that then connects to our supercapacitor used as a battery, and that battery voltage is then able to be read by our easy-to-use patient and physician user interface. Beyond these successes, there are still some future work that we want to do, such as creating a custom piezo material that is better able to mold to the heart model while still meeting our energy requirements, and also integrating with existing pacemakers both for their sizing constraints and their battery usage. We are Cardion, and we are creating energy you can count on beat after beat. We would like to thank Dr. Shaw, Dr. Brulu, Dr. Seedlick, David Reynolds, and the CHOP Catheterization Lab. Thank you, and we will take any questions.
Enjoy the project. When you went through with the testing, I understand obviously you were able to measure, the energy that you were able to save and actually, return to the pacemaker as the heart is beating. But considering that these patients don't always have the healthiest hearts, did you actually also consider testing the reverse, like the actual impact of your device on the heart? Like, does it add any other additional mechanical strain or stiffness that could actually like impact the function of the patient's hearts?
Yeah, that's a good question. When we were focusing on the testing, primarily we were focusing on making sure to test it with the different heart rates, which is why our heart model was able to accurately replicate like all heart conditions, including those patients that already have hearts that don't beat as well on their own. But I think for future work, we would definitely want to see the actual effect of the piezo material, which is why we mentioned sort of making it more custom order to make it fit the heart better. But yeah, that's definitely something that we have been considering for future steps.
So we were planning on placing it on the right atrium because that is where there's the highest outward force. And the piezo material would just be sutured onto the muscle of the heart. So again, it's a little bit hard to test without a physical human heart. But I think given if we can make the custom piezo that can fit more directly onto the heart and also direct the physician to that specific spot, we would hope that they could get reliable data from that.
So we got our initial idea from, I don't know if you've seen in Japan, they have like the walking floors, you walk on it, it bounces, it generates energy. So we also considered like a shoe insert, but for this, it's just so easy to not even have to touch. It simply gets implanted like a normal pacemaker. Patients who live with pacemakers never even notice that they're there. So if ours is able to integrate directly, it just takes a few simple sutures onto the heart. It's already the existing pulse generator, then it should work just fine. Thank you.
Awesome. Thank you, Team Cardion.